Chapter 5, Section 2. We're talking about properties of rational exponents and radicals. We already did radicals a little bit when we were solving quadratics. We worked and talked about radicals, but we mainly just did square root. Now we're going to be talking about any root. Okay, let's review those properties of rational exponents. Basically, it's properties of exponents, but if they're fractional, they follow the same properties we've already done. So a power of a power, or product of a power, if it's the same base, you add. The power of a power, if it's exponent to an exponent, you multiply them together. If it's power of a product, if it's on the outside of a parenthesis, it goes to everybody on the inside of the parenthesis. If they're multiplying together, not if they're adding or subtracting, that would be a FOIL or multiplying situation. Negative exponent does the same thing, drops it to the other side of the divide line. 0 is always 1. If you do a quotient, they subtract. And if you have a quotient and there's 2 a power, it goes to the top and the bottom. It's the same ones we've already looked at, but now it's just with fractions. So we've got to remember how to do fractions. To add them, you have to have the same base. So right now, we're looking at A, 7 to 1/4 times 7 to 1/2. So that's 7 to the 1/4 plus a 1/2. To do 1/4 plus 1/2, you have to have the same denominator. The 4 can't shrink to be a 2, but the 2 can scalar up. If we multiply the top and the bottom by the same number to make them match. If you can make it match exactly, just multiply that one. If they both won't, if one won't become the other, then you're going to have to multiply to the next least common multiple. But the next least common multiple of 2 and 4 is 4. So we're going to multiply the 2 by a 2. We're doing it 2 over 2 because that's a 1, so we're not changing the value, we're just changing the look. So this becomes 1/4 plus 2/4. Top times top, bottom times bottom, which makes 3/4. So that would be 7 to the 3/4 is what happens there. You'd have to have the 4th root of 7 and then multiply it times 3, which there isn't a 4th root of 7, so it's just stuck, just like that. Now, B, they don't have the same base, but they're to an exponent. So this becomes 6 to the 1/2 squared plus 4 to the 1/3 squared because it distributes to both. So that, when we multiply fractions, 1/2 times 2, it's basically 2 over 1, becomes 2 over 2, which is 1. Really, you could just reduce top and bottom. So that becomes 6 plus 4 to the 2/3. 1 times 2 is 2. 3 times 1 is 3. Goes 2/3. There's not a third root of 4. So we leave it just like that. Now, a negative exponent is going to flip that whole parenthesis to the bottom. So now we got 4 to the 5th times 3 to the 5th to the 1/5. That 1/5 goes to both. 5 times 1/5 is 1. 5 times 1/5 is 1. 4 times 3 is 12. Make sure you simplify all the way. Okay. 5 over 5 to the 1/3 is equal to 5 to the 1st over 5 to the 1/3. And when you divide, you're going to subtract. Now, if we're going to subtract 1 minus 1/3, that's a 1 over 1. The next thing that 1 can be is 3. So if we multiply it by 3 over 3, we get 3 over 3 minus 1 over 3. So that's 5 to the 2 over 3. Next one, 42 to the 1/3 over 6 to the 1/3 could be written as 42 over 6 to the 1/3 and then squared. let's see. 6 goes into 42. We could reduce that fraction. So to make this as small as possible, we've actually undone something, and we've removed that exponent on both that's the same outside and brought both into a quotient inside. So we get 7 to the 1/3 squared. So that's 7 to the 1/3 squared, which is 7 to the 2/3. And we've reduced it as much as possible. Try 1 through 4. Give it a pause. Give them a go. Get them as small as you can. Come back and see if they're right. Right, here we go. Number 1, 2 to the 3/4 times 2 to the 1/2. We're supposed to add those together. Multiply by 2 over 2, which makes that 2/4. 3/4 and 2/4, 2 to the 5/4. There isn't a fourth root of 2, so we'll just leave it like that. Let's look at number 2. 3 over 3 to the 1/4. That's 3 to the 1 minus 1/4. Take 1 of 4 away. You're going to have 3 to the 3/4. Number 3. 20 to the 1/2 over 5 to the 1/2 to the 3rd. I would make that 20 over 5 to the 1/2 to the 3rd, which becomes 4 to the 1/2 to the 3rd, which is 4 to the 3/2. Now we could take that a little further, because the square root, remember that could be the square root of 4 to the 3rd, which is 2 to the 3rd, which is 8. So be careful. Don't stop too early. Make sure you find the smallest, most simple answer. And let's look at number 4. 5 to the 1/3 times 7 to the 1/4 to the 3rd. Well, I'm going to distribute that to both. So that's 5 to the 3/3, which is 5 to the 1, times 7 to the 3/4. And that's as small as she gets. There's not a fourth root of 7. Simplifying radical expressions. If it is a radical, you could also express it as a fractional exponent, and vice versa. So that's one way to help you get them simplified. The power of a product and power of a quotient properties can be expressed using radical notation when m equals n over n for some integer n greater than 1. So, product property, if we're multiplying them together, we can separate them, like so. Okay. You can also put them back together. So if you have something to the 3rd root times something to the 3rd root, you can multiply it underneath the same radical sign, and then you can reduce it. Quotient property works the same. You can split them apart, you can stick them together. Okay? You do whatever you need to get it as simple as possible. So, we got 12 times 18, and we're doing 3rd roots. 12 doesn't have a 3rd root, 18 doesn't have a 3rd root, but if we do the 3rd root of 12 times 18, now you can multiply it together and figure out what 12 times 18 is, but you're going to break it right apart anyway. So just imagine like you already did your factor tree. So we're going to break this into, let's see, 2 and 3. This is going to go into 2 and 9. This is going to go to 3 and 3. Actually, that's going to be 4 and 3, and 4 is going to be 2 and 2. So we broke all of those. We have got 1, 2, 3 3s, and 1, 2, 3 2s. So a 2 comes out, and a 3 comes out, which makes it 6. And it was an odd root, so it's just plus. We don't have to worry about plus and minus. Now, let's look at the next one. The 4th root of 80 divided by the 4th root of 5. They've given you a little clue here. Turn into the 4th root of 80 divided by 5, which is the 4th root of, let's see, 80 and 5. 80, 5, those ones, 5 minus 30 is 16. 2 and 8, 2 and 4, 2 and 2, 4 2's. So the fourth root is 2. And technically you'd say plus or minus, but probably only really worrying about the plus version when you're simplifying. Okay, but if it's solving, remember it's plus and minus. An expression involving a radical with an index n is in simplest form when these three conditions are met. Same ones as before. No radicands have perfect nth powers as factors other than 1. No radicands contain fractions. No radicals appear in the denominator of a fraction. To meet the last two conditions, you must rationalize the denominator by multiplying the expression by an appropriate form of 1 that eliminates the radical from the denominator. It's like whenever we're changing a fraction to be able to add them together. We're going to multiply the same thing top and bottom. With square roots, it's easy. You just multiply it by itself because you just need a pair of them. But anything bigger than a square root, you need that index number of that number so that that radical can simplify. So let's look at what we're talking. Write each expression in simplest form. The third root of 135, well, 5 goes into it. Let's see, how many times does 5 go into 135? 135, 5 by 5, 27. 27's 3 and 9. It's 3 and 3. I got 3 3's, but I only got 1 5. So the 3 comes out, the 5 stays in. Don't forget it's a cube root. Make sure you put it on there. Now, the problem here is that I don't have 5 of anything. I got a fifth root of 7 and the fifth root of 8. I got 1 8 and 1 7. Now, what I could do is I could break the 8 apart. And I got 2 times 4, which is 2 times 2. So technically, I've got the fifth root of 7 divided by the fifth root of 2 to the third. This is the simpler way. You could do it by multiplying by 8s. We only have 1 8. We need 5 of them, so you need to multiply by 8 to the fourth in order to simplify that. But we can make it easier, not have to simplify later if we shrink what we have already. So I shrunk the 8 into 2 to the third. I have 3 2's. To get out of the radical, I need 5 2's. So we're going to multiply by what we need, the fifth root of 2 squared. The fifth root of 2 squared. Now, that gets me the fifth root of 2 to the fifth on the bottom, and those are going to cancel out, leaves me with a 2. And on the top, I've got the fifth root of 7 times 4. As I only got 2 2's and 1 7, none of them are 5 of anything. So it's just going to be the fifth root of 28. Just like that. I know you're thinking, 2 goes into 28, can't we reduce it? No, because it's not inside the fifth root. So we can't reduce it. For a denominator that is a sum or difference involving square roots, multiply both numerator and denominator by the conjugate. We talked about this one before whenever we were doing quadratics. We've done conjugates before. All it is the center signs are opposite. Okay? So, write this in simplest form. We got 1 over 5 plus the square root of 3. So we're going to multiply it by 5 minus the square root of 3. But we're going to do it top and bottom. The top's easy, especially with a 1. It's just 5 minus the square root of 3. The bottom's the hard one. I'm going to show you in the box. You could do it FOIL style if you wanted to, but I'll show you in the box. 5 plus square root of 3, 5 minus square root of 3. 5 times 5 is 25. 5 square root of 3, positive. And negative 5 square root of 3, because the negative times the 5 makes negative 5, and the square root of 3 hangs at the end. And then we got negative 3 when we multiply square root times itself. This one and that one reduced to 0. 25 minus 3 is 22. And then we check, is there anything that goes into 5 and 1 and 22? It's only 1, which doesn't help. So that's the 1. Gets a little more complex if the top thing is also a binomial. You've got to FOIL that one as well. Use the box. Use whatever method you like. Radical expressions with the same index and radicand are like radicals. To add or subtract like radicals, you use the distributive property. So we're going to add and subtract like radicals and roots and simplify each expression. Okay? Basically, it's this is bananas and that is bananas. I have 1 of them here. I've got 7 of them there. That makes 8 fourth roots of 10. 10 doesn't have a fourth root. It's got a 2 and a 5, and that's it. So we just leave it just like that. Okay. Here's bananas. There's bananas. I've got 2 of them. I've got 10 of them. That makes 12. 8 to the 1/5. Think of parentheses as a whole thing. The number multiplying in front is how many you have. You cannot multiply the 12 times the 8. You can't multiply the 2 times the 8. You can't multiply the 10 times the 8 because they don't have to the 1/5 on them. The exponent has to come first. So that's as simple as it gets. Now, if we're going to add or subtract, they have to be like things. Cube roots of 54 and cube roots of 2, not like each other. Right now, we've got this, one of them, and we got that, one of them. Yellow and green don't mix, okay? But we can probably shrink this. Let's see, 2 goes into it, 27 times. 3 times 9, 3 times 3, we got 3 3s, so we've got 3 cube roots of 2, that one stayed in, minus cube roots of 2. Technically that's 1 cube root of 2. 3 minus 1 is 2 cube roots of 2, and that's as small as she gets. 5, 6, 7, 8, 9, 10, 11, 12. Here's 8 problems for you to try. Simplify it. Get it as small as you think you can. Push pause. Give it a go. Come back, and I'll work them for you too. Let's look at number 5. The fourth root of 27 times the fourth root of 3. Okay. And just to show you, we can, in Desmos, do the fourth root of 27 plus functions the fourth root of 3, but we get a near rational number. It's not simplified like that, so you got to do the work. So we're going to do the fourth root of 27 times 3. Because they are the same index, we can put them underneath the same radical symbol. Now let's just break the 27. 3 and 9, 3 and 3, 1, 2, 3, 4 3s, so 3, technically plus or minus, but plus is good in this situation. Let's go with number 6. The cube root of 250 over the cube root of 2. I'm going to change that into the cube root of 250 over 2, which is the cube root of 125, which I know is 5. It's on the list. Number 7, the cube root of 104. Well, it breaks into 2 times 52. That breaks into 2 times 26. That breaks into 2 times 13. I'm doing a cube root. There's 3 2s, so 2 cube roots of 13. It's kind of sloppily written here. 2 cube roots of 13. It's as small as it goes. All right, let's try number 8. We're doing the fifth root of 3/4. You can't have a fraction inside there, so we're going to separate it. Fifth root of 3 over the fifth root of 4. Now, there's not a fraction inside, but there's a radical on the bottom of a fraction, which is also a no-no. So we're going to multiply it by the fifth root of, well, I could write this as 2 times 2, so technically that's 2 squared. I've got 2 2s. I need 3 more. 2 to the third. Fifth root, don't forget. 2 to the third and 2 squared makes the fifth root of 2 to the fifth. Those are going to cancel out, leaves me with a 2. And when I 2 to the third up here, 2 to the third is 8, so that's technically the fifth root of 3 times 8, which is the fifth root of 24. And it doesn't go any further than that because it's only 3 2s and 1 3, and we need 5 of each, so that's as small as it gets on those. All right, so that is 5 through 8. Get some space here, and let's look at 9 through 12. A little bit harder because we got to rationalize a denominator. So let's do number 9. 3 divided by 6 minus the square root of 2. We need a conjugate. So we're going to multiply by the 6 plus the square root of 2, top and bottom. All right, so I'm going to do my box here and figure out what happens to my conjugates. 6 and 6 is 36, negative 6 square roots of 2, positive 6 square roots of 2, negative 2. Those cancel. So that's going to be 34. All right, so 34 on the bottom. 3 times 6 is 18, plus 3 times the square root of 2 is 3 square roots of 2. The 3 does not have a 2 that goes into it, so 3 doesn't go into 34, so we are stuck right there. Let's look at 10. 7 square roots of 7 fifth roots of 12 minus a fifth root of 12. That's one of them. 7 of them minus one of them is 6 fifth roots of 12. 12 goes 3 times 4. 4 is a 2 and a 2. I don't have 5 anything, so whoa, hello. That one's done. Let's try 11. 4 times 9 to the 2/3 plus 8 times 9 to the 2/3. 4 of them plus 8 of them is 12 times 9 to the 2/3. There isn't a third root of 9, so we are stuck. And number 12, the cube root of 5 plus the cube root of 40. 4 times 10 is 2 times 5. That's 2 times 2. There's 3 2's. And a 5 left over. So that's the cube root of 5. Nope, that's not how you write that. It's the cube root of 5 plus 2 cube roots of 5. There's one of them. So that's 3 cube roots of 5. Just like that. We're going to break this up into 2 videos.